Here we learn about measures of centrality. The idea is if you have a probability distribution function like indicated here, you would like to know where is the most probable outcome. Where is all the action happening? And clearly in this graph you would say maybe the most things happening in this kind of range here, right? This is where the function has its maximum, and this is probably where the highest probability sits. Now, to make this mathematically precise, we have actually three ways to do this, and we need to learn all three of them because all three of them are used. So there's one thing is the mean value or expected value, which is the average value of all the samples if you sample many times. Then we have the median value, we call it alpha. This is a value so that half the measurements are below and half the measurements are above. And then the mode will be the maximum of that function. And there's absolutely no reason why all these three values should be the same. There will all be an indication of the middle. Let's remove this stuff. So here's the maximum, say, but it's entirely possible that the median maybe is a little bit off and that the expected value is even a little bit off. We cannot expect that they're all the same. And this is exactly what we try to do in this video. And I'm going back and use the soil example, which I have studied in previous videos already. So here is the function again, 192x times a half minus x squared. And then between 0 and 0.5 as the nitrogen concentration in a sample of soil. So let us start with the mean value. The formula for the mean value is integral from minus to plus infinity x f of x dx. It is often denoted by a mu. So mu is for the mean value and is also the expectation of x. That's another way to write it down. But the instructions are clear. We have to integrate this function. The function is only defined between 0 and a half. So then this integral becomes an integral from 0 to 1/2 of x and then times the function 192x 1/2 minus x squared dx. So it's a polynomial integration. I do this step by step. So then we have integral from 0 to 1/2. I multiply the x into the other x, that gives an x squared. I do the square, which is a quarter minus x plus x squared dx. And then I multiply the x squared in there, so then I get 192 integral 0 to 1/2 x squared quarters minus x cubed plus x to the 4 dx. Doing the antiderivative gives me x cubed 12th minus x to the 4 quarters plus x to the 5 fifth. Yeah, and then we sub in the 1/2. Okay, 1/2 to the 3 is an 8th, to the 4 is a 16th, and 1/2 to the 5th is 132. So then we can calculate this all out. It is 192 times 1 over 96 minus 1 over 64 plus 1 over 160. Now finding a common denominator, this becomes 192 divided by 960. I must admit I prepared this in advance. And so then this is a fifth, and a fifth is also 0.2. So we're finding the mean value of this distribution up here is 0.2. The meaning is if we sample the nitrogen contents in the soil many times, then on average we get 0.2 grams per kilogram. Let's move on to the second one, which was median. So the median was the value alpha, so that half the measurements are above and half the measurements are below. The formula is here. So we need to integrate from alpha to infinity the function f of x dx and set it equal to 1/2. Yeah, another fun integration. So let's do this. So then this becomes the integral from alpha to 1/2. Okay, the upper limit is still 1/2. And then the function 192x times 1/2 minus x squared. Let's work out the square. So we get 192 integral alpha to 0.5. And then we get x quarters minus x squared plus x cubed dx. So let's integrate this one, then we get 192. The antiderivative then would be x squared eighth minus x cubed thirds plus x to the 4 quarters. All this between alpha and 0.5. And now we have to sub in these numbers. And here I can use a trick. Because earlier, when I've shown that f is a probability density, I integrated the whole thing to 0.5 and I found the value 1. So this means here, if I sub in 0.5, the upper limit, I get 1. And I only need to worry about what happens if I sub in the alpha. Okay? So this gives me 1 if I sub in 0.5, but then minus everything else when I sub in the alpha. So alpha square eighths minus alpha cubed thirds plus alpha to the 4 quarters. And now all this has to be equal to 1/2, right? So I write this to be 192 times this bracket equals 1/2. Where I worked with the 1 minus 1/2 is 1/2. So then I get this. And then I can divide this by 192. Let's do that also. So alpha square eighth minus alpha 3/3 plus alpha to the 4 quarters is 1/384. But now comes the moment where even an experienced math professor has to use Wolfram alpha or calculator or something of that sort. So this is an equation of 4th order and I cannot find a closed formula right now. So let's use Wolfram alpha. Here's Wolfram alpha, so I type in the formula. Now Wolfram alpha speaks in X language, not in alpha. So I write this formula in X. So x squared eighth minus x cubed thirds plus x to the 4 quarters is 1/384. If I hit return, then Wolfram alpha works for me and it gives me some results. Let's see, I have to scroll up a bit. So then here are real solutions 1 and 2, and then there are complex solutions 1 and 2. I'm not interested in complex solutions, but I'm interested in real ones. I have a negative one and a positive one. Now the negative one doesn't make any sense. We don't have negative nitrogen concentration, so the real important answer is this one, 0.19286. So rounding up, it is alpha is 0.193. This means for the median, we expect half of the samples we measure are below 0.193 gram per kilogram, and half of them are more than this number. All right, and one more friend to do, which is the Mote. And the Mote is the local maximum of the function f. So this should actually be easy. So we write f again by multiplying everything out. 192 x quarters minus x squared plus x cubed. We compute the derivative. So this is 192 times a quarter minus 2x plus 3x squared. And we set this equal to 0 to find the maxima and minima. So we have a quadratic equation which we set equal to 0. So we can use our wonderful quadratic formula. Remember it? Subbing all this in, we get 2 plus minus root of 4 minus 3. All this divided by 6. So then this becomes, if we take the plus value, we have 2 plus 1/6, which is 1/2. If we sub in the minus value, then we get 1/6. So, and then this, of course, is 0.5 and 0.166 in decimals. 0.5 is clearly a minimum of the distribution function because this was the upper limit, right? This was where the function went back to 0. So 0.166 is the maximum. And this means the highest probability is at 0.166. All right, let me summarize all this. So we computed the mean value, the median, the Mote, the 3 M's of centrality. And we found indeed a little bit different numbers. So the mean turned out to be right here at 0.2. The median is 0.193, so rather close, but a little bit different. And then the Mote at 0.166 was even a little bit further away. They're all kind of in the center of this distribution, but they have slightly different meanings, as we have discussed.